In this video we're going to have a little bit more of a look at why baryon number and lepton number are important, but before we do, let's take a step back and identify that in the particle interactions we've covered so far, so when we talk about particle interactions we're talking about anything that could be considered to be a particle. So the ones that I want to particularly relate to here are things like all of the nuclear reactions. So nuclear reactions being fission and fusion and radioactive decay, all of those sorts of reactions. We have already seen with those that mass and energy are conserved. So if there is a difference in mass, we know that that difference in mass was converted to energy. The other thing that we didn't really address at the time because we didn't know about it is the fact that we have these other properties, or one of them we sort of already know. Charge is also going to be conserved along with baryon number and lepton number. So we can go back and have a look now at some of those types of reactions in order to get a sense of how these quantities of baryon number and lepton number, how they are conserved as well. To do that, we'll have a look not at the interactions themselves, but more just some specific examples. So the first example we're going to look at is in beta decay, and in particular beta minus. We said that a neutron turned into a proton. So that was the key fact about neutrons and protons when we're talking about beta decay. And the reaction that we wrote down, I'm going to drop off the mass and atomic numbers here and just write the symbols. So we saw that a neutron became a proton and also created an electron, or a beta particle, and at the time we identified that there was an electron neutrino, antineutrino, that was produced, and we sort of said we weren't really going to talk about it then, we're going to talk about it now. If we look at the charge first of all, note that charge, we usually use the symbol Q, so from this point on I'll be using Q. The charge on a neutron is 0. We know that the charge on a proton is +1. The charge on an electron is -1, and the charge on the electron antineutrino is 0. So we can see that we start off with no charge, the +1 and -1 cancel each other out on the right hand side, and so we are still left with overall conservation of charge. The next one then, next number to look at is baryon number, and again to shorten that we're just going to use the letter B. We know that a neutron is a baryon, so it has a baryon number of +1. Likewise, a proton is a baryon, so it also has a number of +1. Now an electron is not a baryon, so it's baryon number 0, and likewise the antineutrino is also not a baryon, so it also has a baryon number of 0. So in a similar sort of way, though, we start off with +1 for the baryon number, we end up with a total of +1 as well. If we then look at lepton number, and again just to speed things up, we're going to use the letter L. So a neutron is not a lepton, a proton is not a lepton, but an electron is. It has an lepton number of +1, and the electron antineutrino, because it's an antineutrino, its lepton number is -1, so all up we have a total lepton number on the right hand side of 0, which matches the value that we started with of 0. I want to look at a couple of other examples now where we can look at conservation of lepton and baryon numbers, and the next one is muon decay. Now you might look at that and think, hang on, a muon's an elementary particle, how can it decay? So I just want to address this straight up and try and clear up confusion with this particular idea. So far with decay we've basically been considering it as a situation where a particle, or in the case that we looked at with radioactive decay, was a nucleus that split into a smaller nuclei and some other particle that gets emitted. A more complete version of that picture is not so much that it's splitting into or breaking up into other particles. It's more that the mass and energy of that particular particle, along with its charge and other properties, are being reconstituted into other particles. So that's what's happening here with the muon. It's not that the muon is becoming, is breaking up into smaller particles. It is an elementary particle, so the mass and energy of the muon, being much larger than an electron, can be reconstituted into other particles. So what we actually see with muon decay, we start out with a muon particle, and it decays into an electron antineutrino, and a muon neutrino. So we've got those three particles that are produced when the muon decays. So again, it's more the fact that the mass of the muon is significantly larger than the mass of the electron and the masses of the two neutrinos that are also produced. That's what's happening with this decay. Now, if we look at the charge, in this case, the charge on a muon is the same as an electron. It's -1. The charge on the electron is -1, and the charge on the antineutrino and the neutrino are both 0. So again, you can see that the charge is conserved. Baryon number here is pretty simple. None of these particles are baryons, so the baryon numbers are all 0. If we then look at the lepton number of a muon is +1, considering that it is a lepton. The electron likewise is +1. Now the antineutrino is -1 because it's an antiparticle, but we've then got this muon neutrino that has a lepton number of +1. So again, you can sort of think of it as being that these two cancel each other out, and so we're left with the lepton number still being conserved in that scenario. One last example, it's a little bit of an unusual one that we haven't really come across yet. If we look at a proton negative pion collision. So in this case, we're going to be dealing with some baryons, or a baryon and a meson, and so the reaction that we're looking at, or the interaction I should say, it's not so much a reaction here, is the proton colliding with the negative pion, and that interaction produces a neutron and a pion. So again, looking at charge, we know that the proton has a charge of +1. We can infer here that the negative pion has a charge of -1. The neutron has a charge of 0, and the pion has a charge of 0 as well. So you can see on the left hand side those two charges cancel each other out, and then on the right hand side we're left with a total of 0. If we look at the baryon number, so a proton is a baryon, so it has a baryon number of +1. The negative pion is a meson, so it has a baryon number of 0. The neutron is a baryon, so it has a baryon number of +1, and the pion likewise has a baryon number of 0. So again, you can see there that baryon number is conserved. And last one, lepton, again pretty easy here, none of these particles are leptons, given that they are all hadrons, and so the lepton number is 0. One last thing about this particular example, and the reason why I wanted to show it to you, is that in this collision, in a similar way that we were just talking about the decay of the muon, here we're looking at the fact that the quarks are going to be rearranged. So we're not really creating anything new, we're just sort of rearranging what's already there. So if we consider the arrangement of the quarks in these particles, and we'll just make sure we can see that at the top there, the proton has two up quarks and a down quark, as we've already seen. The negative pion, we haven't seen this one yet, but consists of a down quark and an anti-up quark. The neutron, we know, has two down quarks and an up quark. And if we consider what's left, then you can see that we've got two of the downs accounted for, so these two over here are accounted for, and then one of the up quarks is accounted for from the proton. That means we've got an up quark and an anti-up quark that are left over. So that's what the pion would consist of. Now that particular combination, so these two here, that quark-antiquark pair, because we're dealing with a particle and its antiparticle, those two things will annihilate each other. And when we say annihilate, what we mean is that the particles effectively are destroyed, and in being destroyed, they're going to release energy. And as a result, they produce two gamma ray photons. So just one other interesting aspect there of that particular interaction. Now we'll have a look at a few more of these sorts of interactions in class, do a few worksheets and those sorts of things to make sure you're getting a good sense of how these conservation rules apply. One last thing that I haven't yet mentioned, we've talked about the property of strangeness. Now conservation for strangeness is different. We'll actually cover that in a later video once we've gone through the fundamental forces.